So we're going to be finishing our chapter, we're going to be finishing our unit, I think, here. Yeah, it actually is the end of our unit, it's only one chapter here, with a look at what I'm sure is one of your favorite topics, trigonometry. No, I'm not silly. I know a lot of people aren't super crazy about this. You've probably been happy to not think about it too much as geometry, or even pre-calculus if you happen to take a class like that in high school. But here is one of the most important foundational sets of relationships that we have for triangles, and in particular right triangles, that leads to some very useful and unexpected connections. We're only going to scratch the very, very surface of what's going on here, but there is quite a lot that can be done with these things that goes in some directions that you would really never expect. Unfortunately, we're not going to get there, but hey, I'm trying to make a point that it's worth giving some time. Anyway, when we are talking about our triangles, and in particular our right triangles, we have some unique relationships that we can talk about for our sides and our angles there, where if we make C the length of the hypotenuse, A is the length of one leg opposite of the angle A, and B is the length opposite of the angle B and adjacent to the angle A, then besides having access to the Pythagorean theorem, which we've already talked about, we can define some very special functions for describing the connections between these values, between these angles and the side lengths, that the sine function, written sin, evaluated at A, sine of A, is given to describe the ratio between the side opposite to A and the hypotenuse of the triangle in terms of their lengths. That is, sine of A, sin A as it's written, is A, length of that side, over C, length of the hypotenuse. Similarly, cosine is a function designed for describing the ratio of the adjacent side length to the hypotenuse. So cosine of A, cos A, is B over C, and tangent at A describes the relationship between the opposite and the adjacent, where probably what you remember for this relationship, for this set of connections, is the mnemonic so, ka, toa, for picking these three up. But, well, it's all very weird and obscure and convoluted looking right now, why we have these new things with all these new letters, and it's just strange. So I'm going to give a little bit of historical context for where these things come from in terms of etymology and in terms of what they're meant to describe, and hopefully that'll clarify a little bit of what it is that they do and why they have the names they have. So, in order to get there, we need to think about something that's, well, a little bit beyond the scope of our class. We need to think about something in terms of like a unit circle with some of these lines drawn in here that'll explain what exactly they do as we're going. Where we've got that length in the middle there that I use the Greek letter theta to represent. In many math classes, Greek letters are reserved for angles, theta being the most common. Where, with this construction, we can look at that segment QP along with the segment PB, where those two pairs form a special thing with that circle called a chord. A chord is just a non-diametrical line that cuts across a circle. And if we think about those lengths, where we have that the middle to Q, because this is a unit circle, is going to be 1, then if we tried talking about sine of that central angle theta, then sine would really just describe QP. And that is explicitly what sine was originally meant to do. That when we got the name sine, that came through a long and convoluted history from Latin, through Greek, through Arabic, through Sanskrit, with a whole bunch of mistranslations, and I'm not going to bother trying to pronounce some of those words. But the long story short is, sine, etymologically, comes from a word meaning chord. Because sine is meant for describing chord lengths. It's meant for describing lengths of lines that cut through a circle non-diametrically, because when you make those sorts of shapes, you also get that sort of right triangle relationship, but really, The trig functions are for circles. That's more of a pre-calculus thing to think about, though. Meanwhile, for tangent, if we look at that segment CA, we can see there that cutting across on the outside like so, that forms a tangent line, where tangent, again, describes the thing opposite of the angle, so away from theta would be CA, and then below that would be OA. But we're again thinking carefully in terms of what this thing is, that we want its radius to be as nice as possible. We want its radius to be 1. That means that when we're talking about what tangent does, tangent explicitly describes tangent lines. So the name, hopefully, makes a little bit more sense. And then cosine, well, cosine doesn't fit this nice pattern quite as well. Instead, what we have is a different function that we're going to see too often in this class, which goes with cosine, that we call secant. Because if we think about a diameter that includes OQ cutting across the middle diagonally, that would be a secant line. Secant meaning cutting. It cuts across whatever behavior we're trying to describe here, in this case, a circle. Where if we have that OQ and some of those other angles as we want them to be described, secant, 1 over cosine, would describe the secant line OQ better than anything else. So, secant describes cutting lines, tangent describes tangent lines, and sine describes chords. In a sense, those are our 3 original trig functions. Then we get cosine, the one that comes with sine, it's co. We get cosecant, the one that comes with secant, co. And cotangent, the one that goes with tangent. But we're not going to see those other 3, secant, cosecant, and cotangent, quite as much. For one, we can stick to our simpler things here, and then also, I suppose another reason why we're not going to talk about this too much is because unlike so katoa, the mnemonic, what would that end up being? Cho, sha, cow? It just doesn't roll off the tongue quite as nicely. But anyway, it's kind of necessary to talk a little bit about secant to understand this history, and hopefully the names here, well, they have a little bit more meaning with this context. So, getting this development into our minds, let's take a look at a quick basic example for how we can use trigonometry to define some side lengths.